Hello, welcome back. I need to make sure at the very beginning here that you've watched the last section, because what we did in the last section was take this data and bias the average age up. We did not change the spread of the data. We just changed its sample mean. And you saw that that's what makes you reject the null hypothesis. This is what drives everything crazy. Now what we want to do is we want to keep all of the sample means the same, but I want to show you what happens when you just change the spread of the data so that you can see what I'm saying, that when you introduce more error into your data, it can cause some issues. So here's the original data, here's the new data, and I also have this sheet over here, which is the original results. Remember the F was 2.86 and so on, and notice these average values were here and these variances were all calculated for us there as well. Now what I've done is added a cell here, and it's easier to see what it's doing when I add 10. So I'm adding a spread only to the New York ages. Notice what's happening. Originally it was 18. Now I add 10 to that to make it 28. But to compensate for that, I go to the other end, and instead of 21, I make it 11. So I just add 10 up here and I subtract 10 down here. That's going to keep the sample mean the same. You see what I mean? If you have average grades in the classroom, you take one kid on the top part of the mean and you add some points to his score, and you take another kid at the bottom of the class and subtract, then basically one guy did better, one guy did worse, but the average value is going to be the same. And notice what I did here. I took 19 and this 10 here divided by 2 is 5. I added 5 to this one to get 24, but to compensate, I took the 20 and I subtracted 5 to make it 15. And the same kind of thing is going on here. Here I'm adding a number and then I'm subtracting a number. Here I'm adding a number and then I'm subtracting a number. And the middle two numbers I didn't change at all. So I hope that you can see that this really shouldn't change the sample mean. When I add these numbers up and divide by 10, I should get the same sample mean, but the spread of the data is quite a bit different, because now you have a very some high numbers here and some really low numbers, way different than what we had initially. All right, so I should be leaving the sample mean alone. So let's go ahead and redo the test here. We'll go to Data, Analysis. We'll go up here to Single Factor, hit OK, select my data right in here, accept it right there. Labels in the first row, alpha 0.10, everything is correct, and then we hit OK. And then I'm going to go to View over here and Zoom, and I'm going to zoom into 130 so you can see it a little bit better. Now first let's examine the raw data. Before we look at the Anova results, let's look at what's happening. First of all, New York is what we messed around with. The average value is 20.1. The original average value of the data, this is the results of the original data, is 20.1. The variance originally was 2.76, but now the variance is huge. It's 29.03. Notice everything else stayed the same. These averages and these variances stayed exactly the same for the original data. So all that we changed, we kept the average, we kept the actual sample means the same. We just basically, made the data very sporadic and very kind of unreliable in New York. So what's that going to do? When we go down here in Anova, notice the sum of squares between groups. That's comparing how the sample means are differing from the grand mean. That's 24.06. Originally it was also 24.06. It makes sense because we didn't change any of the sample means. But notice that within groups, this is the sum of squares of errors. That is a measure of dispersion of the data, how spread apart the data is inside each sample set. Originally it was 113, but now it's much higher. It's 349. The degrees of freedom stay the same. MST is just this divided by a number. MSE is just this divided by